Well, this is a very interesting function we're going to integrate here. Yeah, so integral of 0 to 1 of the square root of negative 1 raised to the x. It's funny because you have the square root of negative 1 raised to the x. If you try to graph this, there is no function. There exists no real solutions for this. You can actually check this yourself if you want. But let's also observe that we have the square root of negative 1. A number like a real number like that does not exist. In other words, this is actually considered an imaginary number. The square root of negative 1 is equal to I. So we can actually rewrite this problem as the integral from 0 to 1 of I raised to the x dx. And with that, we are now going to actually compute this. So let's actually observe that, well, first you might be thinking to yourself, how can we integrate a number and then raise to a variable? You're scratching your heads thinking, how do I do this? Well, this is complex. Well, now we have the imaginary number I. We're integrating in terms of the complex world instead of the real world. So, we have that Euler's equation is defined as e to the I theta. That's a weird looking theta. That's equal to cosine theta plus I sine theta. And if you look, we said yes, and that means we have I is equal to cosine of what theta specifically? So if we were to graph this in a complex plane, the complex representation number. Complex numbers defined as z is equal to x plus I times y. Your x, if you were to graph a complex number, your x representing from the x-axis and your y, the y-axis, or like the imaginary axis. So this I is equal to z is equal to 0 plus 1 times I. And if you were to graph this, that means I is over here. It's equal to 1, and then it's 0. So that would also have to mean that when we're finding data, it has to be, we're also trying to find the argument. So the argument of this being, if you like pay attention to the unit circle, really, it's actually just pi over 2. Let me write it like this. Data right here, this is pi over 2. So data is equal to pi over 2. I'm just gonna erase this now. So now that you know that, now we know what data is. So now data is equal to pi over 2 plus I pi over 2. We can check this. Cosine pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. So with that, we can write e to the I times pi over 2 is equal to I. So with that, we can replace e to the I times pi over 2 with this, and then we have a new integral of the same thing. Well, same integral, just substitution. That's what I'm trying to get at. So we have e to the I times pi over 2 raised to the x dx, and we can distribute the x into here. So now that then we have this integral from 0 to 1 of e to the pi ix divided by 2 dx. And now integrating this is very simple. So use substitution. I'm gonna stand this way so you can see what I'm writing. We're gonna let u equals pi I times x divided by 2, and do u substitution. Du is equal to, take this in respect to x, it's just pi times I divided by 2 dx. And we want to replace dx for here, so we can just divide pi times I divided by 2. And so that would be 2 divided by pi times I du equals dx, and then substitute that. So we have, and because 2 divided by pi I is actually a constant, we can actually move that outside the integral. So that's what I'm gonna do. This, and then e to the u du, and then integrate that. E to the u is simply just, integral of e to the u is just simply just e to the u. And so we have 2 pi of e to the pi x divided by 2, and then from between 1 to 0. And I'm gonna write it like, and in the next step I'm gonna write it in this fashion, because even though we're evaluate this from 0 to 1, the common factor is 2 pi, so I'm actually gonna take that out. So we have 2 pi I on parentheses, then substitute 1 into here, so it's just e to the pi I times 1 divided by 2, and minus e to the pi I times 0 divided by 2. And we have that 2 to the pi I. This is e to the pi pi times I divided by 2, in which we set that's equal to I, so we could just replace this with I. And then pi times I is 0, so it's e to the 0, which is 1. And this is your answer here, but you're done. But I should be in the numerator rather than the denominator. It's kind of like the same, thing when you're trying to multiply the square root from the denominator and to the numerator. It's the same idea there. So that means I'm gonna multiply the I, and then that would be I squared. So that would be -1. So there's a negative on top, and then multiply the I on the top. So -2i divided by pi of I minus 1. That's our answer for this. Well, okay, so we're not actually done yet technically, because this is data is equal to pi over 2. Now remember what I said before when we were graphing the complex plane of finding what the point representation of I is to find our argument, which was pi over 2. But remember that this is a circle and this is based on periodicity, so every solution is this for every pi over 2 plus 2k pi. So just like before, the graph's small, but don't worry about it. We draw our circle. It's not bad. It's just an example. I'm not trying to be I'm not trying to draw a circle as neat and precise as it is. This is I. So, and this is at pi over 2 when we're trying to find the argument of the point representation. But this also happens at every 2 pi. So for k, it can be any sort of integer. It could go this way, it can go the other way. So we're going to show that as well. So this would mean we would let this, we have pi over 2, but we're also going to add a plus 2k pi for k be any sort of integer. So I'm going to write this e to the I, and then pi over 2 plus 2k pi is equal to I, such that k, for any k is any integer you can think of, positive, negative, even 0. So we're gonna show this for that it works for every periodicity for pi over 2 for every plus 2k pi. And then same as before, we just do this integral 0 1, and then replace this with e to the I, then pi divided by 2 plus 2k pi, and then to this x dx. And then this is literally just the same thing as what we did last time, just distribute the x into here. This rules for exponents, so 0 to 1 of e to the ix. I'm actually not going to distribute the ix into pi over 2 plus 2k pi. It's because this is technically just a constant, so this will make integrating a little bit easier than having to like distribute the ix to the inside of the constant. So I'm just going to leave it the way it is as so. It's 2k pi. Yes, dx. And the same thing as before. We let do u substitution. U is equal to ix pi divided by 2 plus 2k pi. Then du. Oops, that was weird. And we let du equals I and then times pi divided by 2 plus 2k pi, and dx, and divide by both sides. We have 1 divided by I pi over 2 plus 2k pi du equals dx. And this is a constant, so we can actually just move this outside the integral. And same as before, e to the u integrated that is just e to the u, then plug u is equal to this, and then we have this whole thing right here. I times pi over 2 plus 2k pi e to the ix pi by 2 plus 2k pi. And then all this being integrated between 0 to 1. I'm actually gonna rewrite this out as well so that this part is up in the numerator. So what I'm gonna do is I'm gonna find a common denominator. Well, actually, let me first do this. We're gonna multiply the I just like from before, so it's in the numerator rather than the denominator. So if you multiply I, so that means the I is gonna be at the top, and then multiply this again, I squared, so that's a negative. So that means negative I then divided by 2 plus 2k pi. And I'm gonna show my, let's get a common denominator. So we're gonna do pi divided by 2 plus 2k pi. And so that will be pi over 2 plus 2 right here, and then multiply 2 here, so it's 4k pi. And that's simply equal to pi plus 4k pi, yep, divided by 2. And then let's replace this. Let me erase this first. And so this will be negative I times pi plus 4k divided by 2. And so when we're dividing with a fraction, just flip the reciprocal, so it would be negative I over 1 times 2 to the pi plus 4k pi. And so this will equal negative 2i, then pi plus 4, pi plus 4k pi. So that's this. And then same thing applies with this from before. Then we have negative 2i pi plus 4k pi. We're gonna factor this out. It's just like from before because it's integrating from 0 to 1, only plug it into the function here. So we plug 1, so this will be e to the I times 1, then times pi over 2 plus 2k pi, then minus e to the I times 0, pi divided by 2 plus 2k pi. Now this is equal to e raised to the I times this, but that's the same thing as equal to I, so we replace that with I. So 2i pi plus 4k pi. This is just I, and then this is 0, so this whole thing's 0, so it's e to the 0, which is 1, so minus 1. And would you look at that, it is exactly just like these two, except for this part. This is plugging in that k is equal to 0, so if you were to plug k into here, you're gonna get the same thing. So this works for every integer you can pick of when you're choosing your k. This is the solution for this integral right here, these two. And there you have it. I think it's the first time I actually cover something related to complex numbers, so it gets very interesting. You know, real numbers are actually a subset of complex numbers, because imaginary numbers, you know, there's more to it than real numbers. It's a bigger set, is basically what it means to be a subset. So this, two solutions. This is at k is equal to 0, and then this is for any k you choose. That is an integer. So there you have it. Thank you guys for watching. Feel free to check out the last video I did, which was some analysis textbook problem. I thought that one was interesting, so you should definitely check that out. Believe me, it's worth it. So let me know if I should cover more stuff relating to complex numbers, complex analysis, and any sort of this stuff, because I thought this is very interesting to evaluate. So there you have it. Oops, almost dropped that. All right, well, see you guys in the next video.